Welcome to the Unit 7 test remediation packet. We're going to go over some key ideas for Unit 7 to help get you ready for your retest. So the first thing it says is convert the following temperatures into standard units, and the key being standard units. You should realize that the standard unit of temperature is Kelvin. So what we need to do is we need to be able to get all three of these into Kelvin. Okay, so the first one we're going to work all the way through for you. Realize that it's in Fahrenheit, so we've got two conversions we've got to do. We've got to go Fahrenheit to Celsius, Celsius to Kelvin. Okay, once we do that, we'll be in the standard unit, which is where we want. So the first thing we do is we look at the formula for converting Fahrenheit into Celsius. And the formula is this: 5/9 of F minus 32 equals C. In this case, we would plug in our 105 for our F, and you would get 105 minus 32. Okay, we would subtract those two, and when we subtract those two, we're going to get something like 73. So now we have 73 times 5/9 equals C. So you put this into your calculator and you would get the temperature in Celsius, which is about 40.6 degrees Celsius. And then to convert from Celsius to Kelvin, we take our Celsius temperature and we add 273. You can add 273.15 or 273, but generally we just round it off to 273. And once you do that, you should end up getting something along the lines of 313.6 Kelvin. And notice whenever we have Kelvin, we don't put degrees there. There's no degree symbol because it's an absolute. Okay, so now for the next one, you're going to do the exact same procedure that we did here, but instead of plugging in 105, you're going to plug in minus 240. So minus 240 minus 32, and then multiply. And when you do that, you should get an answer of about 122 Kelvin. The final one, you should be able to get all by yourself, and it ends up being something about 373 Kelvin. Okay, if you're having any issues with these, you need to go ahead and see your teacher before you do your retest. Okay, next we're going to say answer the questions below regarding heat and temperature. So the first one says we want to define temperature and heat. So there's a big difference between these two, and it tends to be they tend to be used interchangeably, and they shouldn't be. Okay, so temperature is a measure of average kinetic energy. In other words, if you have molecules in a room, how fast are those molecules moving? Okay, the bigger ones will move slower, the smaller ones will move faster, but what is the average kinetic energy of all the particles in that room? Now, heat requires that you have two different temperatures. So I have one that's hot and one that's cold. And the fact that energy is transferred from the high to the low, that energy transfer is what we call heat. So the only thing that you can really think of it as heat is something has a high kinetic energy and a low kinetic energy, and it's the transfer of kinetic energy between those to equal out. Okay, so it says what direction will heat flow? There's always one direction. It's hot to cold. And then finally, you should have, if you did this properly, 37.5 degrees Celsius. So make sure you understand why this is the case and when it wouldn't be the case. Okay, next it says what method of heat transfer is occurring below in each of these. So you have ironing pans, and one of the things you have is you have direct contact. There's three methods of heat transfer. There's conduction, there's convection, and there's radiation. And of these three, only one of them requires direct contact, and that right there is conduction. Okay, convection has to do with the rising and falling of hot and cold air. And finally, you have radiation, in which no matter is involved. Okay, so it says what method of heat transfer is occurring below. This is convection. We already said this one was conduction. Okay, and you should be able to explain why it's convection. Oops. And then finally it says draw your own scenario in which each method of heat transfer is occurring. So your answers are going to vary based on this, but you have to have one in which they touch. Okay, for example, you could have somebody's foot on the sand. Okay, number two, you have the one where you have hot air rising and cold air falling. Okay, and that could be something as simple as wind. Wind is created when hot air goes up and the cold air comes down and replaces it. Okay, and then finally, number 3, you have to have one in which there is no matter involved. And that could be something like the sun transferring energy to the earth. Okay, next it says, what direction will heat flow? Heat will always flow from high to low, and that is governed by the first law of thermodynamics, which is a restatement of the conservation of energy. Okay, next we get into some more of these calculations, and the calculations can be really complicated. So it's really important that when you do this, you make sure you set up your variable chart and you know what goes with what. In this case, it's what is the final temperature when 400 degrees Celsius, 20 gram piece of metal is dropped into 1 kilogram of 22 degrees C water. So a lot of people, what they tend to do is they say, oh, it's 400 plus 22, and then they take it and divide by 2, and they get 211, and that's wrong. That did work on the early example because it said they had the same mass, so the masses were the same, and it said that they were made out of the same substance. So because of that, when you have those two variables equal, then you can add them up and divide them by 2. But that's not the case here. I have two different things. I have metal and I have water. And I want to keep two separate variable charts so that I know what I'm doing as I go through these calculations. Okay, so the first thing I want to do is I want to say, what is the final temperature? So I'm looking for final temperature. Okay. When 400 degrees C, 20 gram piece of metal. So I know that the initial temperature of the metal is 400 degrees. I know that it has a mass of 20 grams. And then I know that the specific heat is 0.123. Okay, I always know the specific heat of water is 4.184, but that's in joules per gram. So if I want to put it in kilograms, okay, then I can take this thing and I can turn it into a comma. So it's 4,184. Okay, at this point, I know that I have a mass of 1 kilogram, and then I know I have the initial temperature of the water is 22 degrees Celsius. Okay, at this point, I would take a look and I'd say, okay, how can I figure this out? I'm trying to figure out the change in temperature, but I don't have the heat for either one of these. But what I can say is that energy has to be conserved. So the hot object is going to lose some energy, and the cold object is going to gain that same amount of energy because energy must be conserved. So because of that, I can set this up this way. I can say minus Cm delta T equals positive Cm delta T. So remember, the hot object in this case is the metal, and the cold object in this case is the water. So I'm going to plug in my variables using the black side for metal. So I would say minus 0.1, I'm going to get a little bit more room here, minus 0.123 times 20 times the final temperature, which I don't know, minus 400. Then on the other side, I'm going to switch it and I'm going to say that water is red equals, and I'm going to have 4184 times 1 times TF minus 22. So if you look, I have TF and I have TF. One thing that you should realize is that this final temperature of the metal and the final temperature of the water have to be the same because of thermal equilibrium. So because of that, you can treat it just like x, and x is on both sides, so at this point you just need to do the math. So the first thing that I would do is I would go ahead and multiply these two numbers and then distribute it across. And when I do that, it comes out to be something like minus 2.46 TF plus minus times minus gives me a plus 984 equals, on the other side, 4184 TF okay, and in this case it's going to be minus because I've got a positive times a negative, and then it's going to be 92,048. At this point, you would combine like terms. If you look, I have a like term here, and I have a like term here, and I have a like term here, and I have a like term here. So when I combine those like terms, what I'm going to end up with is I'm going to end up with 4,186.5 TF equals 93,032. Now at this point I would just divide. When I divide, I get the final temperature is approximately 22.2. Okay, so that is a very complicated example of how to use specific heat. So you've got the specific heat of the metal, the specific heat of the water, you've got to combine them, you've got to use the law of conservation of energy. In this next case, you don't have anything near as difficult. Instead, what you have is you have just a Q equals Cm delta T calculation. So you don't have to do Q equals Q negative Cm because you're not mixing things. Instead, you're just adding heat to something and you want to figure out what the change in temperature is going to be. You should be able to figure out that the change in temperature is about 91.1 degrees Celsius. Okay, and then finally, in C, you should be able to figure out that it's 16,736 joules. Okay, next we get to heat changing phase. And when you look at the changing phase, it says what is the latent heat of transition for ice? Whenever you have 33,000 joules of energy is used to melt 100 grams of ice at 0 degrees Celsius, and that's really important to 0 degrees Celsius water. Because 0 degrees is the phase transition temperature for ice to water, I know I don't have to add any heat to take it from like minus 10 degree ice into 0 degree ice and then into water. So because I'm only changing phase, the formula is Q equals ml. I have Q, I have 100 grams, which is my M. So in this case, I would have 33,000 equals 100 L. In this case, I would divide both sides by 100, and when I do that, I would get L equals 330 joules per gram. Now notice how there's no degrees Celsius in this case, and that's because there's no temperature in this equation. Okay, the next one, very similar. Q equals ml. You're given the mass, you're given the L, and in this case, you should figure out that the Q value, because that's what you're trying to solve for, is 1,130,000 joules. Okay, next it asks me to sketch a phase transition for water and to be sure and accurately represent the transition temperatures. So I draw my graph, and I'm going to start out here at something like negative 20 degrees. I'm going to have a phase transition at 0. I'm going to have a phase transition at 100 because we're talking about water. And so I'm going to have something that looks kind of like, well, we don't want to zoom in, it's going to look kind of like this. Goes a phase transition, then it's going to go back up. It's going to be a little bit more steep. Excuse me, a little less steep. Let me go ahead and fix that. It's going to go like this, and it's going to be a little less steep. And then it's going to phase transition, and then it's going to go back up again. So this right here represents a phase transition. At 0 degrees, you have a horizontal line that represents when it's melting. And at 100 degrees, and this really should be longer, but I ran out of room, you have 100 degrees because it is vaporizing. Okay, whenever it's changing phase, it's not changing temperature. Okay, next it says the laws of thermodynamics. It says the first law is basically a restatement of the law of conservation of energy. It says heat and work are forms of energy that can't be created or destroyed, just moved around, which is exactly what we're talking about when we talk about conservation of energy. Okay, the second law of thermodynamics says heat, or entropy, always increases, so you have temperature goes from high to low. And no matter what you do, you can never be 100% efficient. You cannot be 100% efficient. And then finally you have the third law, and the third law says that entropy is generally represented by S, is 0 only if you have a perfect crystal at 0 Kelvin. And the problem with that is you can't get to 0 Kelvin. So because of that, it doesn't work. Okay, now you want to represent the equation for the first law of thermodynamics under the conditions below. So the equation we have for the laws of thermodynamics are delta U equals Q plus W. Each one of these tells you a certain thing about this equation. So I'll just pick one and I'll say, okay, isochoric. Okay, isochoric to me means there is no change in volume. And if you first look at this equation, you say, okay, well, there's no volume term. But remember that work has an alternative of this. So you have work equals to pressure times change in volume, which is the same thing as work equals force times distance. You can't do work if something doesn't move. Likewise, if something doesn't expand or contract, you can't do work. So because of that, when I plug in 0 here, 0 times pressure is going to still be 0, and 0 plus Q is going to be Q. So under isochoric conditions, delta U is equal to Q. Now, for the rest of these, you should be able to figure out that adiabatic is this, isothermal is this, isochoric we already covered, and isobaric is this. It says the first law of thermodynamics is a restatement of law of conservation of energy. Okay, if you have any questions or you need any help, go ahead and start your independent practice. And if you're still struggling, you need to seek help from your teacher before you retest.